And welcome, welcome, welcome to lecture number 3, Limits to Growth in the Winter Semester 24-27. Sorry that we had to re-upload the recording of lecture 2 from last year, because it seems like last week we messed up the audio recording, which we could not fix and not recover. But the content for the first, or for lecture 2 and lecture 3 is relatively stable, because it's mostly giving you an impression and starting with some definitions. So we did not do any major changes to lecture number 2, and the same is true for lecture number 3. So I hope that today we're not going to mess it up again, and we will have a proper recording of this lecture. If my voice gets a little bit shitty along the way, that is because I'm still recovering from being sick since last week, but I'm quite positive that I will at least make it through this lecture. So we started in lecture 1 with a general introduction. We outlined 3 key challenges, 1 and 2. We did in lecture number 2, namely environmental pollution and resource scarcity. And today we will look closer into climate change. First, some definitions, like what is climate change in the first place? What's the difference between weather and climate change? How does climate change work? Is it just changing the climate, or what are the underlying factors? And then we will also look a little bit at the effects of climate change, or more precisely global warming in precise number. Like, what does it mean for various key aspects if we have 1 degree global warming, 2, 3, 4, 5 degrees, like trying to give you some numbers from the IPCC report. But before we do that, let's first get started. So we start with some basics and some definitions for now. First, we're going to talk about weather. As of right now, the weather here in Clausthal or in Goslar is, I mean, I've seen worse, I've seen better. It's probably a very German explanation. A few pieces of snow left, a lot of mush and muddy remains, no sun. So that is the weather right now. That is already a characteristic of what weather is, not to be confused with weather conditions and climate. Because the weather is a combination of the current, so right now, meteorological components such as temperature, wind direction and wind speed, amount and type of precipitation, sunshine hours, and so on and so on. The weather is defining a short time period up to several days. So, because we'll later talk about longer time periods, weather, the thing that is outside right now, measured in temperature, how wet is it, and so on, and maximum a few days. So that is weather. Not to be confused with weather conditions, because now we're not just talking about what is outside this building right now, but we're talking about a regional weather statement. Weather condition is the regional weather during a defined time period from 1 up to several weeks. Weather condition is describing typical weather phenomena such as series of thunderstorms in hot summers, foggy month in autumn, or weather conditions which are typical for a specific region and or season. So typical for Clausthal-Zellerfeld is that it's always shitty weather. It's always wet and it's rarely nice weather. I know some people might disagree, but when I was still studying in Göttingen, I sometimes had to go to Clausthal. And I think for the first 3 years, I never had a pleasant day in Clausthal-Zellerfeld when it came to weather conditions. Or not to weather conditions, to weather. So, might over-exaggerating here, but that often helps to memorize those kind of things. So weather, right now, specific locations, maximum few days. Weather condition, regional weather, usually for like a bigger region, and then some typical phenomena there. So those are the first 2 definitions for today. Now, setting that into contrasting that and figuring out what is the difference when we talk about climate. The climate is describing the long-term, at least 30 years, and average weather conditions for a specific region. Example, maritime climate, cold, dry, desert climate, tropical climate. Does someone know what we have here? What type of climate do we have here? So I think we can rule out maritime climate. Cold, dry, desert climate, probably also a bad choice. Tropical climate, also probably not. Temperate climate. Yeah, so weather right now up to several days, weather condition, bigger region, and like the usual phenomena, climate at least 30 years to describe the average weather conditions in this region. Usually a little bit larger than Goslar, so it's not just the climate of Goslar, it's a little bit bigger in terms of a region. That is something that I would really like everyone to tell perfectly apart in the exam. If I'm asking for the difference between climate and weather, this should be like, I should be able to wake you at night and ask you for the definition of sustainability and also what's the difference between weather and climate, because this is one of the key factors that often go so wrong in discussions with people who do not, now I need both hands, believe in a changing climate. Just because there is winter or sun outside or it's like rainy in the summer doesn't mean that we do not have a changing climate. There's this like very famous and at the same time stupid video of senator or governor, some kind of US politician, of course it's a US politician, who picked up a ball of snow, brought it into whatever, like Senate or Congress, wherever he was talking, like, look, there is snow outside, so we cannot have global warming. Excellent. So that's why I would like you to know those definitions by heart, or similar definitions, because once again, those are not like, this is not the only way how you can define weather, weather condition, or climate, but you get the point. Good. So changing climate or climate change, now rather intuitively, is a change of the prevailing climate that we have. Or more precisely, climate change is a long-term change in the average weather patterns that have come to define Earth's local, regional, and global climates. These changes have a broad range of observed effects that are synonymous with the term. So I have a climate that changes over a long term. If I have like one outlier here, that doesn't mean that the climate has changed. So we're averaging all those outliers and then we look at the general trend. For example, the general trend in rising temperatures. Therefore, global warming as one side effect. One of the major drivers for the climate change or for a changing climate is the greenhouse effect, which then causes global warming, so causes the warming of the planet or of our system. It's one of the ways how a climate can change. It gets warmer, it can get colder, it can get more wet, and so on and so on. But this is the one that is usually most often talked about, and those things are often also interlinked. So if it gets warmer, I have either a tendency, depending on where I live, that it also gets wetter or drier, or that the amount of rain in certain time periods heavily changes, even though the average over the year stays the same. So they are somehow interlinked very often. And very often as well, we use global warming and climate change synonymously. So if I do that by accident, sorry about that. Usually I'm trying to really tell it apart. Okay, this is like now I'm talking about climate change and now I'm talking just about global warming. But it happens very often that people just use those synonymously, even though it's not quite correct. So main driver of a changing, or an example of the changing climate is global warming. Global warming being primarily, or like a big chunks being caused by the so-called greenhouse effect. This being the simplified version now, we'll have a few more slides following. So we have this nice thing called the sun up there, which lets sun beams pass to our planet, making it livable in the first place. So we have some kind of energy radiation coming in. Some of it being absorbed by the surface, by the water bodies, and so on and so on. Others being reflected from the surface, going pushed back into the atmosphere or back into space. And as you can also see, some of the back radiation that is reflected from the surface are then pushed back to the planet if certain molecules or atoms are present in our atmosphere, and those are namely the famous greenhouse gases. We'll also get a definition of those in a few slides. The most famous and most infamous, I would better say, representative of those greenhouse gases are CO2 emissions, but there are also other greenhouse gases, but we'll come back to that later. So one of the causes being sun radiation energy coming from space to our planet being not fully reflected there, but sunlight being either absorbed by the planet itself or being caught in the atmosphere, that causing our system to heat up. Global warming is the long-term heating of Earth's climate system observed since the pre-industrial period, so 1850 to 1900, due to human activities, primarily fossil fuels burning, which increases heat-trapping greenhouse gas levels in the Earth's atmosphere. So we're not talking about natural global warming, that like natural processes are either cooling or warming the planet or our atmosphere. We're talking specifically, when we're using this term, about warming effects that humans cause. So like, this is also where this phrase or term comes from, like human-made climate change. We're not so much concerned in the long run with natural deviations of the climate, but more with those that we caused, and also primarily since we started doing industry on a heavy level, because those are mostly fucking with us. The term is frequently used and interchangeable with the term climate change, though the latter refers to both human and natural produced warming and the effects it has on our planet. And as I also said, it's just like mostly about the warming part. It is most commonly measured as the average increase in Earth's global surface temperature. So a little bit simplified that we're only looking at the temperature, but it's a quite good measuring stick. It is similarly simplified as like that we only use CO2 as the main indicator for greenhouse gases in our atmosphere, even though there are others. So now, similar figure to what we have seen before, now just with more details. And it's a self-study star, so you don't have to learn it by heart. It's more to give you an intuition. Also, don't get caught up on the numbers explicitly like shown there. It's essentially to give you a little bit of intuition of what types of energies either that we create or that come like from space are contributing to a warming planet. So once again, our sun sending quite a lot of energy to our planet. So that's the big arrow that we have over there. I would really like to have a measuring stick myself, but I'm probably not going to get that. Some of the solar radiation that is coming in is directly reflected by clouds or the atmosphere itself, so it goes straight back into space, not our problem. Another part is directly reflected by the surface. Different parts of our planet's surface are better or worse at reflecting solar radiation. Ice is quite good and nicely reflects light. Less ice on our planet means less capacity to reflect additional solar radiation. And then there's some parts absorbed being by the atmosphere and the rest is being absorbed by the surface. So we have a big chunk coming in, some of them being directly reflected, most of this being either absorbed by the atmosphere or by the surface. Then we also have internal energy that's coming from our planet, so emitted by the surface somehow. Some of this is absorbed by the atmosphere. Some is also emitted by the atmosphere in different ways. So there's quite a big chunk of energy also being like created on our planet in natural ways. The big problem starts here, that almost all of the stuff the big chunk of what we absorb, or that it's like coming through, and also from the things that we emit ourselves, is reflected directly back to us due to the greenhouse gases in our atmosphere. On one hand, or like back in the days, that was quite helpful because it helped to warm up the planet, to make it livable in the first place. And it also is going to remain livable for a lot of species in the long run, just maybe not quite nicely for us. So this is like, initially it was a good thing. We just have to, like, we're messing with the balance that worked quite nicely in our favor for quite a while, and we're tipping the point where it might end up very ugly for us. We also, it's really hard to read on that bad beamer. What do we have here? Thermal convection and latent heat, some minor stuff that you can essentially ignore on the side. Main takeaway, and this is why we kept it a self-study slide, is radiation coming in from the sun, from the outside, some parts being reflected, some being absorbed, and we are also emitting quite a lot of heat. Some then goes straight out and is not our problem anymore. A lot of them being reflected by the atmosphere, mostly due to greenhouse gases, thereby ending up back again. And if you would have a perfect balance, planet would, like, oversimplifying heavily here, but if we would have a perfect balance between incoming or essentially created energy or emitted energy incoming to the Earth and the stuff that we're sending back, then we would pretty much stay the same. The more heat we trap inside our atmosphere or on our planet, the warmer it gets. It's like it's boiling water, essentially. It's super simple, but I'm oversimplifying also heavily here because otherwise people wouldn't have like separate study programs just for all the atmospheric stuff and doing their PhDs and so on and so on. I'm just a computer scientist and I'm trying to make a point here. Thank you very much. Good. Global warming being something that we can observe very nicely, especially after the pre-industrial era, is something that we heavily focus on because this is essentially where we kicked off this global warming part significantly. And in this illustration, which is a quite common illustration for annual mean global temperature changes, you have 1 year as one stripe. Blue intuitively indicates like a rather cool temperature. The more you go to either white or then towards the red scale, it indicates more of deviations towards being hotter from this mean temperature. And as you can quite clearly see, initially a lot of blue, and it's getting more red, and my brain might not be functioning quite well. So you can quite nicely see in this very, very simple visualization that there is a trend towards a higher temperature, a higher annual mean global temperature. So not just for a specific place, but for the whole planet. You can also, of course, make this more specific for particular regions on a planet. Here we have selected, because we're in Germany, the temperature change in Germany, not from the 1850s, but rather from 1961 to 2010. We have a baseline of 0 degrees, and initially we have quite a lot of deviations to the bottom, which are indicated by the blue ones. So somewhere here around 1890 or so, we actually deviated almost -2 degrees from the mean temperature. But you can also similarly see the same trend, that it's getting successively hotter and hotter and hotter. That we're very rarely now deviating in a direction where it's like colder than the average temperature. But still, like, it's a really nice example to go back to this climate change and global warming definitions. It's like just 1 year where it's extremely cold does not mean that the general trend is not there, like to have like a warmer climate or a warmer global temperature. Just because we have one very cold winter or one very cold year actually, doesn't mean that there is not on average rising global temperature. So just because it's cold outside today doesn't mean that we don't have global warming. So this is why it makes sense to look at data on a longer time scale. Now let's briefly have a look into the proper definition of greenhouse gases before we continue looking into some of the effects, especially in relation to climate change. So, not climate gases. Greenhouse gases are those, I still don't know how to pronounce it, gaseous. The native speaker puts in a strong word for gaseous. Constituents. Okay, let's start. Greenhouse gases are those gaseous constituents of the atmosphere, both natural and anthropogenic, that absorb and emit radiation at specific wavelengths within the spectrum of terrestrial radiation emitted by the Earth's surface, the atmosphere itself, and by clouds. This property causes the greenhouse effect. So what we have seen in the two figures before, that we have this back reflection from the atmosphere to the surface, thereby causing the atmosphere and the surface to warm up, is essentially this greenhouse effect. And the different types of greenhouse gases that I can have in that atmosphere are multiplying this effect. There are different types of greenhouse gases. Water, vapor, being the first one. Carbon dioxide, probably the most famous one. Nitrous oxide, methane, and ozone are the primary greenhouse gases in the Earth's atmosphere. There are more, but those are the ones that we should, or that we usually care most about. I do not have the exact number in my head right now, but not every greenhouse gas is essentially the same. So you cannot interchange like one carbon dioxide for one methane, and like they're not causing the same amount of damage. If I'm not mistaken, probably Chintan can Google that real quick. Methane is something like 30 times more climate damaging than carbon dioxide. If I'm not totally wrong, at least like it's a multitude of that. So releasing just a little bit of methane has a multiplying, like the multiple effect of like the same amount of carbon dioxide being released. Come on, Chintan. Okay, so I was off a little bit. So the first source that Chintan found was 1 to 11. So 11 times more dangerous. Don't nail me down on that number. Just wanted to make the point that they are not all the same in terms of their damage potential. They vary. And various greenhouse gases occur naturally, but as we said, like water vapor is quite nice. Also carbon dioxide also appears naturally, but we're not concerned with the natural emission of greenhouse gases. As we discussed before, we're only concerned with the human-made greenhouse gas emissions, which then cause, are part of this global warming and climate change disaster. And there is very often, especially in Germany and other industrial countries, this attempt to defend themselves why they are not doing more to essentially mitigate climate change or at least limit climate change. They're saying, look, we're such a small country. If China does something or the US does something, like what does it matter that we as Germany do something, or we as the Netherlands, or the UK or France or whatever, like pick any country you like. But historically speaking, we are among the top 10, I think even top 5, 2, 3, top 6, close, emitters of greenhouse gas emissions if you look back to the start of the Industrial Revolution. So USA and China, sheer size and industrial power being at the top there, Russia, Brazil, Indonesia as well. But Germany, quite far ahead for such a small country that supposedly can't really do anything about it because we're just too small and too insignificant. What you can also see, besides the billion tons of CO2 emitted by those countries, is that they are differentiating here between land use and forestry as like one category, the green one, and fossil fuels, cement as other categories. And Brazil and Indonesia are having a quite big part of this green bar, so meaning a lot of their CO2 emissions, for example, coming through land use or forestry, or in their case, deforestation, for example, destroying the Amazon forest. So like you can have different ways in how you essentially help contributing to this mess. You can also, of course, further narrow that down and look at greenhouse gas emissions per capita, meaning per person living in a country, because then you don't have this line of reasoning saying, okay, China is just that big or India is just that big, they have 1 billion people and more. Of course, they're going to produce or cause more greenhouse gas emissions. But if you look at it per capita, per person living there, then you can very easily also compare it to smaller countries. And there is a very drastic difference between the lowest emitting countries and the highest. Not sure if you can read that very nicely from the seats there. First place, Middle East, because they are also simplifying here, but like oil, fossil fuels are essentially like close to being for free there. And you also need a lot of infrastructure to keep Dubai or whatever even livable if you have plus 40 degrees there. So you need a lot of stuff to keep this all going there. But there are, of course, like also other factors. But usually the oil producing countries are not among those who are fossil fuel saving in their daily life due to the cheap availability of fossil fuels. But they're not really making a big dent here. We are more concerned, for example, with the US, China, and where's Germany here? Somewhere here in the middle. So sure, we're not emitting per person as much as the US people do, or even as the Chinese do, but we're still emitting way more, for example, than the Indians do. And there is the populations, like on the x-axis, so we have 8 billion people. The wider one of those rectangles is, the bigger like the population for this particular thing. This is why, for example, the Middle East is that small. And up, essentially, we have the emissions in tons per year per person. So for the Middle East, we have something north of 30 tons of CO2 or of greenhouse, not CO2, of greenhouse gas emissions per person. The mean average is the blue line, roughly 6.6 tons. The median is just below 5. And we would get or need to get significantly below that to somehow, or we should have done that like decades ago. Now it's more or less too late. We shouldn't have been like significantly below that number on average for everyone, so that we somehow keep the climate in balance. So 30 tons, totally unacceptable. Even 6.6 tons or even 5 tons being too much. In Germany, like it's not a specific number there, but I'm guessing something around 7, 8, 9 tons. We'll get to that as part of our homework, if I'm not mistaken. Another way to look at this greenhouse gas emissions in the context of the industrial revolutions is the concentration of greenhouse gases, or more precisely in this moment, in this like example, CO2 concentrations over a long period of time, because one of the other defense mechanisms that a lot of people have is that this is not human-made climate change. The warming is not caused by anything we did. We are just so insignificant, we could not even change the climate of this planet. And it has, or it changed already many, many times over the existence of this planet. And the later part is true, as you can see here in those circles. So you have on the X scale a time axis with thousands of years ago. On the right one, you have the CO2 contrition in parts per million. And you can see that there were times in those ice age cycles where it went up and down and up and down and up and down. Total natural fluctuation, something just shy of 200, going sometimes up to 300, somehow averaging, I guess, I'm eyeballing this now, between 250. And that is fine. It, of course, means that species need to adapt, and the environment looked different. Like when you had ice age in Germany, it was a little bit like Clausthal nowadays, usually not very pleasant and often cold. But in other times, the climate was warmer, you had vast forests and so on and so on. So of course, like, it changed stuff, but it was a natural occurrence, which from our standpoint today would be fine because we can deal with that. And it also stayed fine like that, essentially just until 1750, where we were more or less in line with this natural fluctuations. But this amazing big chunk just at the end of this part, like, you can see the green stuff going up a little bit, and then the black part where we blew past the 400 parts per million. I'm not quite sure where we are right now. I'm not sure if we already crossed the 500 parts per million, but we're on a good path if we didn't do so yet. This is the part where what we are concerned about, because this is clearly, at least if you're looking almost a million years back, not part of this natural fluctuations anymore, or at least there's a very good case to be made that this is not part of the natural fluctuations anymore. Because all those cycles, we have seen them before, looking back 1 million years. And I would argue, like, looking back more years than 1 million is rather irrelevant for us as a human species, because those were times, like, a million years ago, nothing like us existed, so not our problem. So what is relevant for us is, like, this part here. How did they get those CO2 concentrations? They essentially drilled into glaciers and took samples, and then you could measure from those samples of ice, you can measure the CO2 concentration in those ice cores. Good, so good case to be made that this is not a natural cycle, just going slightly offhand, but rather a human-made problem that we are causing here. And it's not just like a nice linear, slightly increasing line that is a little bit going up. It's like all those crypto guys would say, to the moon is essentially where we are heading with our CO2 concentration. Of course, there is like a natural upper limit, and it's not exponential, even though it looks quite exponential on the curve, but it's definitely significantly more than what we have seen in the last 1 million years. So, big problem. As I already mentioned at the very beginning of the lecture, is that the warming of, or the increase of the global average temperature is not just a single thing, a single effect that happens isolated in itself. It just gets warmer, everything else stays the same. If the global surface temperature gets warmer, it also has effects on other parts of our weather system. So the amount of water evaporating, dry seasons, the amount of rain falling, and so on and so on. So those are like complex interlinked systems. And some of those systems can also have so-called feedback effects on each other. Those are processes that can either amplify, so multiply, make bigger, or diminish, make smaller, the effects of climate forcings. A feedback that increases an initial warming is called a positive feedback. A feedback that reduces an initial warming is a negative feedback. Any suggestions for examples? Okay, wildfires. If it gets warmer and at the same time also less rain, stuff gets more dry, I have more wildfires. It burns down the, let's say, rainforest that was very tropical and wet and kept stuff wet. Then it burns down, it does not have the capacity to hold moisture anymore. I have more wildfires. Oversimplifications, but one example. The ice albedo effect is also one of those. Albedo being the measure of the diffuse reflection of solar radiation, essentially what I said before, ice nicely reflects solar radiation. If I do not have that ice anymore, so if I have melting ice, it lowers the albedo and increases the absorbed solar radiation. So to give you an example, for example, from Greenland, where you have quite a lot of glaciers, a nice white glacier reflects a lot of solar radiation. As soon as you start to have melting water bodies on that glacier, they're usually like dark bluish color, they start to absorb more energy. The darker something is, usually the more it absorbs, but the water also reflects the solar radiation worse than just the ice. So you have those water bodies on the glacier, they absorb more energy, thereby they're causing more warming of those glacier parts. You get larger water bodies, they absorb more energy, which then contributes to more melting ice and so on. So essentially you have this ever self-increasing cycle. Same goes, of course, for the Arctic ice, either at the South or the North Pole. That's like same part, even though the North Pole is mostly like, the South Pole has more like continental mass under it. But still same, the less ice I have on the water, the less likely I'm being like to get the same amount of ice back, because solar radiation is warming up the oceans and so on and so on. Less is reflected, same cycle. Another example is thawing permafrost, so unfrosting of stuff that has been frozen permanently for quite a while, especially, for example, in Siberia, where you had parts of the soil being frosted for enormous amounts of time. So they actually built like complete cities on frosted ground. And now that all of this is thawing, buildings start to shift, which is like one problem for those people living there. Another problem is that a lot of those permafrost soils have a lot of methane stored. So now due to global warming, they are thawing, which means they release methane, which contributes, as we learned, as part of the greenhouse gases, to global warming. More permafrost thaws, releases more methane. You get the idea. So those are examples of feedback effects. The warming ocean could also be another example. We have different temperatures in different regions of the oceans, which then are, once again simplifying heavily here, part of the reasons why we have, for example, something like the Gulf Stream that transports warm water from the Gulf of Mexico to roughly Iceland and Norway. Collapses there, goes down to the deep part, takes cold water back to the Gulf of Mexico, and there's essentially like a flow of an exchange of heat, nutrients, water, and so on and so on. There is a very, how do I say that? Scientists are getting more and more concerned that this Gulf Stream, or the scientific name is AMOC, could potentially either at least decrease its transport capacity, which would be bad for us because then we don't have this energy, this heat exchange anymore, but also it has quite a profound impact on everything that lives based on this system, or that it either could completely collapse and disappear. That supposedly happened in the past, but not in time frames or scales that were relevant for human existence. So no one really had to deal with those effects. There are very strong discussions how weak or how much this stream was already weakened, what a decrease of X% would mean, what a complete collapse of the AMOC would mean. Therefore, it's like very hard to give proper statements about it, but it most likely will cause an extreme drop in temperature for everything that is currently benefiting from the warm water being brought up here from the Gulf area, from the Gulf of Mexico area. So less energy being brought to us, meaning quite drastic drop in temperatures here. Whether they're going to still be livable or not depends on the amount of the decrease of the stream. Whether it's even possible when it collapses is a different discussion. What this shows is that very, very complex system that seem to be rather stable over time can come very close to a very, very tiny tipping point that then makes a huge difference in terms of drastic changes in our environmental system. It also shows that global warming can make stuff very, very cold. If certain parts of a very complex system that makes this planet still livable for us suddenly don't work the way they used to work in the past. So another another example for a feedback effect, because the global warming changes this existing stream, the AMOC, thereby causing another change in the climate, probably towards the cold part. And there are many, many more. There are actually whole lecture series on feedback effects, so I think we have added some links to the resources later, but I just wanted to give you some examples. On one hand, global warming being interlinked with other effects is not a standalone thing that you just observe and then have to essentially take a shirt instead of a pullover or a hoodie, but also like some examples on how this can compound the effects of the global warming that we already have. A very famous way to measure the greenhouse gas emissions per capita, per person, or per population is often this carbon footprint, where you take CO2 essentially as an equivalent of greenhouse gas emissions. So you take your CO2 emissions, and if you're not emitting CO2, you're essentially trying to find equivalents to that CO2 emission. So as we discussed before, Chintan said the first Google source gave him methane is 11 times more dangerous or more harming than CO2. If you're emitting methane, you're essentially just calculating this in equivalents of CO2 emissions, and you do that essentially for all the emissions that you cause, and then you have the carbon footprint. It's a measure of the exclusive total amount of carbon dioxide emissions that is directly and indirectly caused by an activity or is accumulated over the life stage of a product. So you can make that for a product, for a service, for a human being, for a population. It essentially gathers all those emissions caused by a certain thing. And at least one person in this room already knows where unexpectedly the carbon footprint came from, because you might have at least my initial impression or initial thought was, okay, someone who tried to make people understand how much emissions they are causing came up with this idea to say, look, please calculate your carbon footprint. Here's a formula, here's a tool, here's a way to do it. And then you understand how much greenhouse gases or CO2 you emit in comparison to someone else to make you reflect on this. That was not the case. The first step to reducing your emissions is to know where you stand. Find out your carbon footprint with our new calculator and share your pledge today. British fucking Petroleum, one of the worst polluters on this planet, tried to sell you the responsibility of saving the planet. And I think we had this slide before when we discussed the 100 companies that produced more than 70% of the world's greenhouse gas emissions since 1998. BP is on fucking place number 11. They emitted 1.53% of all the greenhouse gas emissions in that 30-year period. And nonetheless, they are starting a marketing campaign to make sure that you, and you only, are aware of the damage that you do to the society and to our environment, and that you have to do something. Definitely not BP, who is drilling up all the fossil fuel that we are burning. So unexpected source of the carbon footprint calculator, or the concept of this carbon footprint in the modern sense. My voice is breaking up a little bit. I'm still trying to finish this. Another interesting insight from this list is that, of course, all of them are somehow heavily in the fossil fuel business. So there is not a single company on this list, if I'm not mistaken, that has nothing to do with somehow emitting fossil fuels, because it's just extremely profitable business, which also makes it even more counterintuitive what you often have like as some kind of weird discussions or allegations that, oh, you're just into climate protection or you're just advocating for climate change because they are paying you to do so. Last time I checked, on the Forbes list of all the billionaires, there was not one person on that list who made their fortune with something truly sustainable. And nope, I'm not counting Elon Musk as someone who cares about sustainability, not for his private jet or for the fact that he's really just interested in selling as many Teslas as possible. What we discussed before, consuming less being the most sustainable thing we did. We're coming back to Matti's example at the end of this lecture. So there's not a single billionaire who made a fortune being sustainable and acting sustainable, truly sustainable. So yeah, so it's just more profitable to ruin this planet. Do it as long as you can if you still want to get rich. For whatever reason, the microphone turned off for a second, but welcome back. Good. So, long tangent, sorry about that. Sometimes I get passionate. So, the idea of the carbon footprint. I hope no one is muting me all the time. Chintan is smiling really suspiciously. Good. The point, so like unexpected origin story of this carbon footprint in the modern sense, still the idea of being aware and having some kind of a very, very rough estimate, because this is by no means a very exact number, but having like an idea like how much damage do I cause to the society, boiling that down to one number can be a helpful tool. Like of course, and we'll get, for example, to life cycle assessments in a few lectures, and then also to like an invited lecture from David Inkerman, like with a particular focus on this, like how can you assess the damage that actions that you do have on the environment, either by consuming a certain service or a product and so on and so on. But this carbon footprint being like, due to its simplicity, quite nice to put yourself into perspective, like how much damage do I cause and how much would I be allowed to do if I only take my fair share of the damage we can cause to our planet within a given time span. Maybe one last word or like sentence regarding the last statement there. On one hand, of course, it's absolutely outrageous that the worst or one of the companies among the worst polluters and destroyers of our environment tries to blame you as an individual for destroying the planet, and that you should do something while trying to not be responsible for anything like that they do. On the other hand, I'm not rejecting that everyone has a responsibility. Like you all have a responsibility to do something. Companies do as well, especially since companies are not just magical being that exist and we cannot do stuff about it. They are made up out of people. If people working for BP would decide to not work for BP anymore, BP would not emit any greenhouse gas emissions anymore and would not produce any oil and other fossil fuels anymore. Of course, it's not that simple. There are economic forces and means, people like food and maybe shelter, and there are reasons why people still work for BP and so on and so on. But just saying you as the individual are at fault is as wrong as to just say only those companies are at fault. It is way more complex, and you have to be a little bit aware of those like different dynamics there. So back to the CO2 footprint. So it is too high on average. So we're emitting too many greenhouse gas emissions, or in particular CO2. So the goal would be getting it down. If we get it down, everything should be fine, right? Once again, not quite as simple, but there are a lot of companies that are promising to do all they can to reduce their carbon footprint or even remove their carbon footprint completely. So in 2020, Microsoft, for example, promised that in 5 years from now, or soon 4 years from now, Microsoft will be carbon negative, and so that means that they are not even emitting carbon as part of their operations, they're even removing carbon. And by 2050, Microsoft will remove from the environment all the carbon the company has emitted, either directly or by electrical consumption, since it was founded in 1975. So they don't want to have just like a negative carbon emission for each year, but they also want to have so many negative emissions that they made up for all the damage that they did in the past. Unfortunately, that promise is no longer true because they noticed building all those AI data centers causes quite a lot of CO2 emissions and operating them as well. So they scrapped most of their... I have no idea why BBB mutes me all the time. So they scrapped all of those, or most of those goals. I'm not quite sure about that, but essentially it was a nice marketing gig that sounded good back then when sustainability was hip and cool, but they never followed through with it. Apple being pretty much on the same stage here. Apple today unveiled its plan to become carbon neutral across its entire business, manufacturing, supply chain, and product lifecycle by 2030. The company is already carbon neutral today for its global corporate operations, and this new commitment means that by 2030, every Apple device sold will have net zero climate impact. Yeah, that never happened. On one hand, the claim that they were already carbon neutral for the global corporate operations depends heavily on what you account for and what you don't account for. You will get a better idea of what that means when you have done the life cycle assessment lecture. Essentially, it boils down to every statistic is as good as, like, in German the saying is, jede Statistik ist nur so gut wie sie gefälscht wurde.
Interpretation of the statistics.
Yeah, the interpretation, like essentially, only trust the statistic that you created yourself to prove your point and no other statistics. So depending on what you leave out or what you put into that statistic, you get different numbers, and the Apple statistics are very heavily debated. Probably doesn't give me a seat on the board of Apple anytime soon or a high-paid job at Apple, but I guess since this is the 4th or 5th iteration of this course, those chances have decreased every year. Good, so similar claim from Apple, same bullshit story. They also noticed that all their AI and whatever stuff and all the producing cheap stuff in Asia, then shipping it across the globe and building products that don't last a single year does not really help you in terms of sustainability. Polestar, a battery electric vehicle manufacturer, also made some statements about climate neutral cars. We're embarking on our greatest journey so far, challenging ourselves to create a climate neutral car by 2030 by reducing emissions throughout supply chain and production. But they also noticed that they might have a problem there. Relying on the current trend of offsetting by planting trees is not sustainable in the long run. It would mean using too much land, and the long-term carbon storage capacity of forests and soils is not well known. Offsetting by planting trees also risks contributing to monocultures, so just planting one type of species, and loss of biodiversity. Additionally, there can be no guarantees that a forest won't later be lodged, devastated by forest fire, or altered by climate change. So, to their credit, they noticed rather like directly that there might be problems with the current advertised way of reducing your carbon footprint. When you're flying to New York and you're just planting a tree, that neither does account for the carbon emissions that you caused, nor is it a long-term thing that works if we like scale this up for all carbon emissions that we're causing, because there's just not enough space on this planet to plant all those trees. That's the first problem, like you need to plant trees somewhere. And then you also have this problem like monocultures, which is bad like for biodiversity and for other reasons, like they're right about that. But there's also no guarantee that someone is not gonna cut down this forest at some point to then use the timber or use it to heat up your home or do other stuff. This only works if you plant the tree and it stays there. It doesn't work if you do anything else afterwards with that tree. Like sure, in some way or another, if you use it as building material and it stays compacted and that's able for discussion. But first point, not enough space to compensate for all the CO2 emissions that we're causing to get to carbon neutral. And also you have to make sure, even if you would have enough space, that it really stays in that tree and doesn't go anywhere else. So still probably a greenwashing goal, but at least they were aware of some of the shortcomings that they had there. And of course you can like try something like CO2 removal tools, no, not tools, factories or something, essentially building machines that remove CO2 from the atmosphere, and then you can try to store it somehow. So there are like test sites in Iceland where they're pressing this, where they're trying to essentially put this into the very porous, like in the volcanic stone stuff. So essentially that it stays in there and somehow mineralizes. There are also ideas that you can push them just into caverns that were like, for example, old like salt caverns or where gas was in before. You take the gas out, burn it, put the CO2 back in. But it's extremely energy intensive, which usually then causes further CO2 emissions or other greenhouse gas emissions. It's extremely expensive and it only works on a small scale. Thus far, all the operational facilities on the planet don't make a relevant dent while still causing quite a lot of greenhouse gas emissions and being extremely expensive. So I'm not going to say that this might not work in the future, but we'll get back to that at some point when we talk about the limits of technology and complex societies. Good. That's just like a side story. So planting trees has its limitations. Removing CO2 from the atmosphere has its limitations. The best is to not just emit them in the first place. So we're back to this consume less thing. But the other problem is it's not just only about CO2 emissions, because CO2 emissions is just what we are most comfortable measuring our environmental damage in, because like we're used to that concept from this carbon footprint or from just news articles where we always talk about CO2 emissions or greenhouse gas emissions in general. I briefly touched up on this when I criticized Microsoft and Apple for their statements about carbon neutrality. What you have besides CO2 emissions is of course also everything that goes beyond like energy into their products. And when you build a product, it's not just energy that goes in there, you also have to put a lot of resources in there. Where do you get those resources? Sure, you have to mine them somewhere, which causes CO2. You can put that into your statistics again, but it also causes quite a lot of environmental damage, as very well established by these old mining facilities just outside of this building. You have to dig holes, or you have to drill into a mountain. You have to use various chemicals to separate the ore from the relevant materials that you want to have. You also leave a lot of undesired materials out there. So you're essentially causing quite a lot of environmental damage by just extracting them, by driving them through the globe, across the globe to manufacture them, then to sell them, then to use them. And once you're done using them, you throw them away, often, as we discussed with the recycling initially, not in a very sustainable way, because recycling is quite hard and has a lot of disadvantages or challenges in itself. So all of these things also need to be accounted for on top of just the CO2 emissions. So it's not just about being carbon neutral by some magic means of removing all of our CO2 emissions and somehow getting rid of them. Then you still have to figure out ways to somehow mitigate, prevent, adapt to all the environmental damage and resources that you're using. And Sorry. Both Microsoft, Apple, but also most of the big tech players who manufacture IT devices or electronic devices in general are not really good examples for designing their products in such a way that they either last long or that they are easy to repair. So this is like one company called iFixit, but there are also others who do like similar things. They essentially offer either repair equipment or repairing IT equipment or electronic devices for you. So you can either buy the equipment from them to do that yourself, or they are going to do it for you. And they are also rating popular electronic devices by their repairability, and a score from I think 0 to 10 if I'm not mistaken. 10 being extremely good repairable, 0 means once something breaks, it's a piece of waste. Simplifying here again, but you get the idea. And for most of the products of the big players, there is a prioritization of design and aesthetics over repairability. So, for example, batteries that you cannot remove anymore. I'm old enough to remember smartphones where you could take out the battery. I think I have one of the very few smartphones left where you can actually replace the battery. It's like one of those fancy Fairphone things. But most smartphones nowadays do not allow the normal user to just remove a battery, which means once your battery sucks, you can either buy a new smartphone, which is usually encouraged by the sellers, so Apple and so on, or you have to do extra steps to find someone who can do that for you, and you have to pray to God that it doesn't cost you the warranty for your smartphone. The same is true for all kind of other damages. Like what's most often damaged on a smartphone is usually the screen. It just falls down once and then you have a spider interface on your screen. Usually Apple tells you it's more expensive to fix it than buying a new phone, or it's almost as expensive as buying a new phone. You still can get someone to do it. Then they somehow have to figure out a way to get the screen out first. Very often it's glued onto other components by design, because glue is just more nice instead of screws, because screws don't look that nice. Also, when I glue it together, I save some space, but it makes it very hard to repair something. Apple also at some point made it even harder to replace the screens, because they had some kind of mechanism to identify unauthorized repairs, and then suddenly your phone didn't work anymore, even though it had a perfectly fine new screen. So they're claiming in a lot of cases that they very much care about the environment and that they want to be very sustainable, while at the same time building the most shitty products just for 1% of extra aesthetically pleasing design or whatever. Like, it's not like there are not ways to build a proper, nicely usable smartphone without gluing everything together and making it unrepairable, and even if it is repairable, then putting like extra artificial road blockers there so that people cannot repair their stuff anymore. So their actions and their words do not really align. Usually we talk about this, or we call that greenwashing. Good. That was once again slightly depressing. What did we cover thus far? Definitions of weather, weather condition, climate, climate change, global warming, greenhouse effect, feedback effects, and I might have forgotten one or two other things that we discussed. We also looked briefly at the carbon footprint. I think you either already calculated as a homework or you will calculate it as a homework now? It's done already, so that was just a little bit of background knowledge for you. What we're going to now look at, given those greenhouse gas emissions, how much time do we have left to do something, given certain thresholds. So to do something, like already teased that in the first lecture, 1.5 degree global warming is almost gone, or is practically gone. We'll get to that on the last slide. But also, what do certain degrees of global warming practically means in terms of, for example, weather conditions or weather phenomena that make our life usually more difficult. So, first of all, we're gonna come back to these greenhouse gas emission figure that I showed definitely in the first lecture, maybe also in the last lecture, where we had this illustration that showed you, okay, so if we want to get to 1.5 degree global warming, this is how greenhouse gas emissions have to develop. If we want to get to 2 degrees, this is how they have to develop, and so on and so on. Essentially, the one figure where we got this information from, that we're currently heading towards something like 2.8 to 3.2 degree global warming. That was a simplified figure, because there's usually not one pathway for a certain CO2 emission level. And this is where we are now extending the complexity of that one figure earlier. What you can see here is, once again, up to something like 2020, roughly 2021, the historical data of how many gigatons of CO2 we are emitting. And then we have differently colored pathways to still make it to 1.5 degree. And those pathways represent different probabilities that we will make it there. So for example, the red one, which seems to give us the longest time frame and allows us to emit the most amount of CO2. So it essentially is the pathway that calculates, or that tells us with 900 gigatons of further CO2 emissions, we could make it to 1.5 degrees, but only with a probability of 17%. If I ask you to board an airplane with a probability of 17% to make it to your destination, you would probably tell me nope. So let's try a different number. Let's take the blue bar, or the blue line. If we emit 650 more gigatons of CO2, we have the chance of roughly 33% to make it to 1.5 degree global warming. Who's going to take that airplane with a 33% probability of making it to the destination? Still not so many customers. So 500 gigatons give us 50%, 400 gigatons give us 67%. Do I get more customers from my airline? Still not really. Okay, 300 gigatons give us 83%. And the more you reduce it, the more likely it is that you get to actually 1.5 degrees global warming. So it is not just like one fixed number. You see that those models working on a probabilistic approach, usually you only get only one line, because those figures are already difficult enough, and usually you focus on one particular information at a time or two that you would like to convey with the figure. But it's important for you that you understand this, because this is sometimes the underlying reason why there are different predictions. Of course, it could be different models, but even within a model, given different assumptions or different probability levels that you're fine with, you're getting to different results. And 83% with 300 gigatons to 17% with 900 gigatons is a huge difference. Good. So we learned something new. Given that we were emitting something like 45 or just shy of 45 gigatons in, I think this figure is from 2020, and they assume that for 2021 is also roughly the same. 300 gigatons, 83%, I guess we're getting somewhere closer to the probability where you will get onto my airline. Let's say we have those 300 gigatons that we can emit, and then afterwards nothing. That would give us 6 years, 5 years, 6 years, something like that, if we are not increasing our emissions, and then suddenly nothing. So within the 6 years, if we do like 45, 45, 45, 45, maybe a little bit more, then 0, or we have to slowly but surely getting less, and then somehow getting to 0 over a longer period of time. Bad news is that is not gonna happen. We're still, at least for 2025, we're still in the period of rising CO2 emissions, so we did not even get down here. That's the bad news once again. Chintan muted me again. Good. Which brings us back to some uplifting quotes. The popular idea of cutting our emissions in half, in 10 years only gives us a 50% chance of staying below 1.5 degrees and the risk of setting off irreversible chain reactions beyond human control. This is essentially a different way of illustrating this airplane example with a 50% survival rate that I just gave. And I mean, for if you're like now an 80-year-old person, like you probably don't care that much. But if you have to somehow continue living on this planet, like 50% doesn't really sound like a good deal. Like no one would jump on an airplane if you have a 50% survival rate. Like no one would do that. Another way to nicely phrase this is like watching a car crash in slow motion. I always like this metaphor, but instead of hitting the brakes, we're essentially flooring the gas pedal and accelerating, because this is what we're doing when it comes to CO2 emission. Instead of really reducing them, we're still increasing them. Yeah. The results are well known. Namely a global average surface temperature that increases. This figure I find particularly interesting because it dissects the observed temperature and separates it by human and natural drivers and only natural drivers. So we have the observed temperature that goes up. If we account for human and natural parameters, it quite nicely matches there. If you would have only the natural drivers, we would be somewhere around the zero where we started off, slightly higher sometimes, but somewhere in the ballpark of the natural fluctuation that we would expect, but we're quite clearly off. You can also see like those light shadows in the background here. Those are essentially the, neither remembering the English nor the German word, essentially the uncertainty levels here, like what we had with the different probability levels there. Like you also, like when you're modeling this, it could be in this range. So these like background colors are essentially showing you what range those fluctuations could be. There is a very interesting website that I find particularly interesting. Unfortunately, I cannot show it to you during the lecture because it's not compliant with the license that we have for our lecture materials, but I highly encourage you to click on that link and play with that website a little bit yourself. It essentially takes known German cities and moves them on a map to existing places that you might be familiar with to give you an idea how the climate in those regions will change. So for example, Hanover will have somehow the climate that you right now experience or that we used to experience in the south of France in the Côte d'Azur. And I think Magdeburg will have something like the southern part of the Pyrenees Mountains in Spain, so northern Spain, southern Pyrenees Mountains, and so on and so on. So it's quite interesting to put in perspective, this is where I'm living now. I might have been to this place for like being on vacation or whatever. I have an idea what the weather is there. And this is how it's going to be where I'm living at the moment or where I might live in the future. And then also the implication, what does it mean for the south of France, for the Côte d'Azur? Like, what's the weather going to be like there? If the Côte d'Azur is now in Hanover, what's the weather going to be there? So it's a very interesting website. Good. This is a figure that I was previously talking about. Now, I think we're going to, if I remember the slide order correctly, we're going to explore what it means if we're not getting to 1.5 degrees, but rather to 2 degrees, or to 3 degrees, or to 4 degrees global warming. What does that practically mean based on the IPCC report's estimates? This is just like the reminder that we discussed that we should somehow stay below 3 and at best between 2.7. But here are now some really nice examples. So we already discussed that we will have an increase in extreme weather events. Those could be heat waves. This could be too much rain in a short time. This could be droughts where we do not have enough rain over a longer time. Various types of extreme weather events, and now there are some examples that illustrate how more often or how much those extreme events would either occur in terms of numbers or how more extreme they would become. I think in the first lecture I made this example that a 100-year flood should occur once every 100 years. In various regions, due to climate change, those suddenly appear once every 10 years. And the 10-year flood that is supposed to appear once every 10 years suddenly appears every other year. So using this logic, we're now looking at some of those extreme weather events. For example, a 1 in 50-year extreme heat wave is supposed to happen once every 50 years in our scenario at 0 degree global warming. 1 degree global warming is already not true anymore. Chintan could please make a note that we update that number because we're way past 1 degree global warming. So slide number 49 needs an update. At 1 degree, it's already 4.8 times every 50 years. So from once every 50 years, it's more or less now at once every 10 years. At 2 degrees global warming, it is 13 or almost 14 times in every 50 years. And at 3 and 4 degrees global warming, we're getting closer and closer to making this once in every 50 years, so more or less once in a lifetime, if you're lucky, heat wave occurring more or less regularly on a, even at 3 degrees, it's essentially getting a biannual thing, that you have a once in every 50-year heat wave. Australia being known for being sometimes quite hot, so we brought some examples there. In January 2020 was Sydney's hottest day on record, 50 degrees, and the number of days hotter than 35 degrees based on 3 degree global warming would look like follows. So they had one day with 50 degrees in 2020, those would become more regularly. Then it's not a record thing, then it's just a new normal thing, that you have days that are actually 50 degrees global warming. And I guess no one or very few people watching this lecture have, including me, have any idea what it means to have 50 degrees global, of a temperature outside. That is probably not really bearable for a long period of time, or even for a short one. Anyway, besides the fact that we cannot really understand this sitting here in Clausthal or Goslar having snow outside. So number of days hotter than 35 degrees based on 3 degrees global warming. So for Sydney, it would be 11 days instead of 3 days per year where we have more than 35 degrees. For Melbourne, the number would increase or also almost double to 24 days per year instead of 11 days. So getting close to a month of temperatures with above 35 degrees. For Darwin, a particularly fucked place, we would get to 265 days instead of 11 days per year. If you have, I'm not quite sure about the numbers in Dubai or Saudi Arabia or whatever, but essentially Darwin will be a completely different place than it is right now. And despite, or in addition to just illustrating the increase of those extreme weather events, this slide or those examples are also supposed to fulfill another purpose. It shows that even though they're on the same continent, and Australia is fucking huge, that different regions will be impacted differently by those extreme weather events, especially in times when it comes to how often, but also to what extent they are influenced by those extreme weather events. There might be places who are totally fine and have absolutely no problem. The weather or the conditions might become actually a little bit nicer on average for those peoples. Other places are really fucked. Biodiversity as another example. At 1.5 degree global warming, we will lose 70 to 90% of the coral reefs worldwide. At just 2 degree global warming, which we're definitely heading for right now. Remember, we're roughly at 2.8 to 3.2. 99% of the coral reefs on this planet will die. So we're most definitely going to lose all the coral reefs on this planet because we're just not doing something. Might not be your problem because you're not a vivid diver and you don't really care about those coral reefs, but they have quite important roles in existing ecosystems that in the long run will definitely influence you. Rain, either more or less, is also a common problem. At 1.5 degree global warming, 70% of land will face extreme rainfall and average rainfall events, and average rainfall will increase by 2%. Sounds about right, like extreme rainfall for almost 20% of the places is like quite, maybe not quite nice, but increased rainfall on average 2%, that sounds about right, that's okay. At 2 degrees, we'll have pretty much doubled those numbers, but just half a degree of global warming doubles the effect. We are going for 2.8 to 3.2, so we are increasing those effects even more. Droughts, essentially the other side of the coin for too much or little rain, will also significantly increase. On one hand, we can look at this on a global level. So at 1.5 degrees, the average drought length is roughly 2 months, then 4 months, and at 3 degrees, we're getting to 10 months. But I can also look at this for specific regions. So let's first take Europe apart. There are some areas that do not really suffer from this drought problem. Northern Europe, for example, right now has no significant droughts. There are usually 0 months of droughts, and even at 3 degrees, the longest droughts that they might expect is something like, or the average droughts, sorry, not the longest one, are about a month or so. In other places, like Southern Europe, where it's already quite dry in many, many places, we will have 3, 6, and 12 months. And an average drought of 12 months means 1 year without a single drop of rain, which is quite a lot and makes it quite hard to grow food, not even speaking about having water to drink. I mean, Tehran is now, or Iran is now considering evacuating Tehran, their capital, a multi-million people city, because they're running out of drinking water. Think about moving Berlin because we're running out of water. First of all, where to put them? Where do we have sufficient amount of extra water? And where do we put everyone who's living in Berlin? We cannot just put them on the campground outside of Goslar. So this is like a tremendous, like that, Iran is far away, but this is something tremendous that you're not really realizing as long as you're thinking about like how would we actually do that? How would we move Hamburg? How would we move Berlin? How would we move Munich if we have to? And who would want them? So droughts on average getting longer, some places being more affected than others. And there are, of course, also on this sliding scale, extreme cases. North Africa would be extremely unlucky. At 1.5, we're already talking about an average drought length of 7 months. At 3 degrees, we're talking about an average drought length of 5 years. 5 years on average without a single drop of water. And it doesn't mean that after those 5 years, we're suddenly having the rainfalls of our lives and everything will be great and go back to normal. Nope, this will happen regularly, that we go without water for 5 years. That also means that you cannot feed people there anymore. You can also not provide drinking water for people anymore. This is essentially becoming an inhabitable place on this planet. The people have to go somewhere. Go to places where it's still livable, but where we then are having to figure out ways to live with more people on less space and also having less space to care for all of those people. Like if we double the amount of people living in Germany or Europe, for example, we'll also need to figure out ways to produce twice as much food. We would need to figure out how to handle twice as much waste. We would need to figure out how to provide twice as much drinking water. And I mean, sure, some politicians have a quite easy answer to that. We just close the border and shoot everyone who gets close to it. But we might also be at some point on the other part of this like discussion. If Europe or parts of Europe become uninhabitable, sure, you can try to then say, okay, Germany first or whatever, but there is an end to this logic. So just shooting everyone is not really a well thought through plan. Good. Yeah, so I already like triggered or like teased the water scarcity problem a little bit. We already have various people who have to deal with water scarcity at 1.5. It's going to be roughly 250,000. Sure, those numbers might not be quite accurate in terms of like plus minus 10, 20 millions, but that's not the point. 2 degrees, we're adding roughly 50% to the population who's threatened by water scarcity, and this goes on and on and on, and especially water as an extremely relevant, scarce resource then also, of course, has a lot of conflict potential. But it's not just the weather that's going to suffer from, or not the weather itself, but also like essentially our daily lives, and it's going to suffer from global warming, but also the poor economy is going to suffer, which intuitively should be a reason for most of the economy people to finally do something about it. But I guess it also pays well to destroy the planet and then try to rebuild it later. Global GDP in 2100, so like the overall thing that one country produces, or like the planet produces, is supposed to go down by 8% if we remain at 1.5 degree global warming. At 2 degree, we're already deducting minus 13% here. And just like one example in terms of economic damages, for example, by floods, at 1.5 degrees, by flood damages or from sea level rises, we have $10 trillion damage. Sure, it's a really good business to then rebuild everything that was just lost, and you can create quite a lot of money from this. And if this happens regularly, you have a very nice income stream. But on a planet with limited finite resources, this story somehow has an end to, you cannot do that indefinitely. And at 2.0% global warming, you're adding essentially another trillion to this number. If you're looking at river floodings in some European countries, Germany, UK, and Hungary, you can see a steady increase of the damages. So Germany quite linearly, or not quite linear, but essentially like slowly but surely increasing. The UK seems to be suffering quite heavily already at 1.5 degree. That probably is the case if you're essentially an island in the middle of the sea, and then also having quite a lot of rivers. So they're already starting with a quite high number of damage increases, but 4 degrees really then kicks it up a notch. Hungary has a little bit of a weird relationship. Like they're starting extremely high with like 3,000% of economic damage increase by just 1.5 degrees. And suddenly by 2 degrees it goes a little bit down. I cannot really explain it because I'm not really an expert on the flood damages in Hungary. But then once again it goes up. So it could be that there's like a little bit of a, like it's still increased by 2,500% at 2 degrees, but there seems to be some kind of effect that buffers is a little bit in this weird frame for Hungary. But you would need to please talk to someone who's an expert in flood damages for Hungary in particular, why that is the case. Good. Let's close this session with the final, or one of the final statements from this IPCC report. A century of rising emissions must end before 2025 to keep the global heating under 1.5 degrees Celsius, beyond which severe impacts will increase further and hurting billions of people. So that means, as of today, we have 1 month left to fix all those problems. I'm updating this figure now, or this number now, every year. It used to be 36 months or 37 months. Then we're suddenly at 25 months. Then we're at 30 months. And now, finally, we have 1 month left to save the planet. Next year, I'm not quite sure what to do, honestly, because I'm not really expecting, I would be pleasantly surprised if the last month of 2025 suddenly gives us a really nice turn of history. I'm skeptical, but we'll see, and then next year I have to somehow figure out what to do with this slide. And that's it for today. So initially, in the first part of the lecture, we covered some basic concepts and definitions: weather conditions, climate change, what is partially causing climate change and who is causing it, keeping the natural drivers and the human-made changes or drivers separate from each other, greenhouse gases and the greenhouse effect. Something we talked about. We also talked about this energy balance. We talked about feedback effects and a few other concepts. We also looked at the different effects of global warming on different weather conditions, phenomena, or just on the economy. What does it mean if we have 1.5, 2, 3, or 4 degree global warming? What does this mean for the inhabitability of certain places on this planet? What does it mean for those that are still inhabitable when a lot of other people would also like to live there instead of dying, and so on and so on. Next on your watch list is now the 4th lecture, which is, I think, something like the limits to growth and planetary boundaries. In that, you will have so essentially you're watching it at home. You will get to the point that to the source that inspired like the first part of the name of this course, The Limits to Growth, a book that was also essentially for me, something like 20 years ago, the first introduction to this topic. I'll probably say more in that lecture video. There will also talk about some underlying dynamics of modeling our planet in terms of resource consumption, population, and different constraints. And we'll also introduce the concept of the so-called planetary boundaries. So essentially 2 things or 2 major topics that you will watch at home. And then we will be back, if I'm not mistaken, for the circular economy lecture. Could that be true? I think so, and if that is the case, then we'll have our, Chintan is nodding, that's good. We'll have our first invited lecturer. Annie Melkonian Gottschalk is a professor here at our university. She will introduce herself in more detail. That's not my task. She can also do it much better than I probably. And she will be here with us as the first invited lecturer. And then we'll have like a few more lectures with invited speaker who can explain their field of expertise much better than I can do that. So we'll cut off the recording now. Some more sources that you can look up. Questions, as always, in, let's say, 10 minutes from now. So we'll continue 10 minutes before 4 p.m. again. That gives me a little bit of time to relax my voice. And yeah, thank you very much for watching. I really hope that we have a proper audio this time. We'll upload it as soon as possible. Thank you very much. See you next week. And please stay for the Q&A session. Thank you very much.